All right, so first, some announcements. The first is for SAC, the Student Activity Committee. So again, these are undergraduate representatives of supposedly all of the undergrads, right, who perform actually some key roles within our department. Including helping to evaluate the tenure case. I don't know if any of you know, I'm up for tenure this year. So I was evaluated by the SAC last year. But that's one of the roles that they perform, as well as just advising, just generally when the department needs the advice of the students within the department, we talk to SAC. So we had two nominees / candidates from the junior class, Lexi and Michael. Michael has indicated that he does not want to serve, but would like to thank whoever nominated him. Does that still hold true, Michael?
I mean, if I get voted in, I'll do it.
A stunning, rousing candidate speech. Is Lexi here? Oh, okay. So now's the point where I'm supposed to give you 1 to 2 minutes to introduce yourself as a candidate and convince your classmates to vote for you. What's that? All right, so vote for whoever you see fit. Use this. I don't think I'm allowed to formally endorse anyone, right? So use this form, this link. I'll send it out as a Canvas announcement as well, so you'll have it in email. Presumably, it might be easier to follow than from these slides. But the link is in these slides. And vote for your classmate. Okay. Less fun news. I have gotten 4 emails from people in the class. I know everyone in the class should have gotten an email from University of Utah Contact Tracing. But I've gotten 4 emails directly from students who've let me know that they've tested positive for COVID the past week. Looks like we're having some kind of an outbreak right now, unfortunately. We are the University of Utah's got current guidance on this, which you should have seen in that email, is to wear a mask on campus for 10 days following exposure. I think that takes us through Monday's lecture. If you consider that we're probably all about to get an email about Friday's exposure as well. Yeah, so you should have gotten one about Wednesday's exposure. They're always behind, so we'll probably get an email about Friday's exposure. There's some trigger where we will have to go to online teaching, which I know none of us want. I don't want it. You don't want it. But we may get there, so watch out for that announcement. And I would send out a Zoom link to do live lectures online. Yeah. Yeah, that's a good question. I heard 3, which we're definitely over now. I heard 5, which we're not over yet. And I have no idea what the time frame is, right? So my best indication is that it's like 2 on Wednesday, 2 on Friday, which is 4 in a week. But we'll certainly pass 5 before the end of the semester, but that doesn't make any sense, right? So I'm not sure. I really don't know. I wish I knew more, but I don't. Yeah. Anyway, I wanted to remind you, testing is available on campus. The recommendation is get tested within 5 days of being exposed. You can pick up a test kit from the engineering main office, the dean's office. They just have like a little box with little plastic bags and tubes, the spit collection tubes. Follow instructions to fill and register the test. You can use your phone, and then drop it off in the red box, which is not labeled last time I saw it. But in the little confusing, but in the entranceway, like the entrance vestibule to WEB, there's a red box on the wall. That is the sample collection box, and you'll get results back. I did this last week. I've just been doing asymptomatic testing whenever I'm teaching, and I got results back that afternoon. They might be under a crush of tests right now. So, any questions on any of this or anything else that's more pleasant before we get started? Okay. All right. Thank you all. And I'll be bringing in masks while we're under this. Okay. So to pick up where we left off. So we were talking about mass conservation, right? So we started with Reynolds transport theorem. We derived a general equation for conservation of stuff, right? We said we're going to let B equal some property of the fluid, and we derived an expression for conservation of that or balance of that stuff. And now we're asking the question of what happens if B is mass, right? So what if we're looking at mass? Mass is conserved. And so we end up with this form of the expression. Last time we looked at this slide, so this is not new. We said we're going to look at the steady flow assumption where the all partial derivative with respect to t are 0. And so this means that in terms of mass conservation, this means that mass entering and leaving the control volume will balance exactly. So sum of outflows equals sum of inflows, right? Any mass that leaves must have come in from someplace. And in general, if velocity varies across inlets and outlets, I said this is the way that you would find the mass flow rate across those inlets or outlets. Right? So now we're going to consider the case of uniform. Your text calls this 1D flow. I found it a little bit confusing, so I'm trying to use the uniform notation on these slides. But uniform flow basically just means that we're assuming that the velocity is constant across the cross section or control surface. This is not always the case, okay? And we are going to one of the kind of special cases that we're going to consider in mass, momentum, and energy balances are what happens when the velocity profile is not uniform. Okay. But if we do assume that it's uniform, it simplifies things quite a bit. So outflow minus inflow in this uniform case, uniform steady case, implies the sum of rho A V over all of the outlet control surfaces is equal to the sum of rho A V over all the inlet control surfaces. Okay. Meaning the mass flow rate over one of my control surfaces is rho A V. That makes sense? All right, so the density times the area times the velocity would then be the mass flow rate over that control surface. So in this example, if I have, let's see, 2 inlet control surfaces, 1 and 2, and 1 outlet control surface 3, this steady uniform flow assumption implies that rho 3 A3 V3, right, the outflow, is equal to the sum of my inflows, right? Rho 1 A1 V1 plus rho 2 A2 V2. Yes. The area is the cross-sectional area of the inlet, whatever the inlet is. In this case, the pipe coming in. Yeah. Not the control volume inside, right? This is area. So A1 would be the area across which I have that velocity V1, the flow V1. That's correct. Any other questions? Okay. Okay, so and you'll get some practice on that in the homework, which will be assigned today. Another case in fluid mechanics, a special case, is so-called incompressible flow. An incompressible fluid is one that does not change its density based on the applied velocity or based on the motion of the fluid itself. So in our mass balance, if we have incompressible flow, we're going to assume that density does not vary at all, right, in space or time. So we're going to have d rho dt equal to 0, right? No change in density. D rho dx, d rho dy, d rho dz, all equal to 0. Okay, so we're going to treat rho as constant for an incompressible fluid. And this is going to greatly simplify our mass balance, right? This is actually going to greatly simplify a lot of our equations. But first, I just want to get you all talking just a little bit, and you may not have really understood or been introduced to the concept of incompressible fluid or compressible fluid previously. But I still would like to get some discussion on what we think are compressible versus incompressible fluids. So a compressible fluid, right? That's something where the motion of an object through the fluid can cause the density to change. And in an incompressible fluid, if we move an object through the fluid, the density does not change. Okay. So just based on maybe some intuition about fluids you've dealt with in the past, I'd like you to, or if you've read the textbook, that would help as well. But that's not required here at all. Okay. I just want to get you thinking about some these different types of fluids. Talk in groups, 2 to 3 students, just a couple minutes, because this is a new concept to many of you in the class. Examples of incompressible and compressible fluids. Okay, so please discuss. What do you get for one or the other?
Incompressible fluids, volume density would change if those things in the liquid state, water.
Sure.
Gases, volume change.
Are there any cases where you could treat a gas as incompressible?
Off the rip, I'd say ideal gases or something that more truly dense gases.
So in ideal gases, we have, right, PV, nRT, right? So I don't know, we typically think about density changing. Yeah, we'll come back to that. Yeah, we'll come back to that. All right, we're gonna call it there. All right, who can give me an example of an incompressible fluid? Yeah, Michael. Hydraulic fluid, brake fluid, right? Has to be incompressible for a hydraulic system to work. Yeah, in fact, a hydraulic system is not working often because you have air intrusion, and then the air inside that system is compressible, therefore causing air bubbles in the system cause it not to behave as expected. All right, what other examples of incompressible fluids? Water, right? Generally, we think of water as an incompressible fluid. Density is constant, even down to the deepest reaches of the ocean. Density changes by something like less than 2% with the enormous amount of pressure. So we can pretty safely treat water as an incompressible fluid. Other examples of incompressible fluids that you all came up with? I heard a more general statement over here. Would you say about what do you think of as generally an incompressible fluid? Yeah, so something like most liquids, right, we treat as an incompressible fluid. Okay, so compressible fluids, gases, right? Generally, a lot of the time, we're going to treat gases as compressible fluids. Are there any cases where we can treat a gas as incompressible? Not an inert gas. Doesn't have to do with reactions. Has to do with speed. So at high speed, so if we have gas at high speed, then we're going to treat it as compressible. But at low speeds, for example, air, we're going to be treating as incompressible. So for air at low speeds, we treat it as incompressible. We're going to talk quite a bit more about this and how we get to this relationship. For example, in the last chapter of the text, yeah. So it's low speed relative to the speed of sound. That's what really matters. Yeah. So what do we mean by low speed? So we mean low relative to the speed of sound. So it's another non-dimensional number. So in general in physics, but fluid mechanics is kind of a branch of physics. If we want to know if something is important, right? We want to know if the space between molecules is important. What number do we use to figure out if the space between molecules is important? First day of class. Knudsen, Kn, right? So we compare the length scale to the intermolecular spacing. And we said that generally in this class, the length scale that we're going to consider is much larger than the spacing between molecules, even the spacing between air molecules. And so we're going to treat fluids as a continuum, right? Because it's not like we're trapped in a bunch of boulders flowing down a mountain, right? We're dealing with this soup of molecules that are so close together that the space between them doesn't matter so much, right? So we had a non-dimensional number that tells us whether or not that was important, right? So here again, we have a non-dimensional number that's going to tell us whether or not the fluid can be treated as compressible. In this case, it's called the Mach number, and it's the velocity, the characteristic velocity that we're dealing with. So basically, how fast the thing is moving, divided by the speed of sound. And if that velocity is low, right? If the Mach number is low, typically less than about 0.6 or so, then we're going to call that low speed, and we're going to treat it as incompressible. Okay. What this is basically telling us, I'll get to questions in 1 second, okay? What this is basically telling us is that if we have a fluid that's traveling fast enough, so the speed of sound tells us how fast pressure waves travel within a fluid, right? So I have pressure waves coming out of my mouth and going into my microphone. So it's going on the Zoom recording, or you all are hearing it. And that's traveling at the speed of sound, right? Those pressure waves are traveling at the speed of sound. But if we have let's say an object moving through the air at something close to the speed of sound, that means that pressure waves from that object cannot get out of the way of the object fast enough, and the response of the fluid is to change in density as that object moves through the air at close to the speed of sound. So as we're high speeds, we're going to have to consider compressibility effects, but at low speeds, we're going to be treating air and other gases as incompressible fluids. Yeah, I mean, if we were moving at close to the speed of sound, which is incredibly high in liquids, if we were moving at close to the speed of sound in liquids, then we would see compressibility effects. So we could start seeing things like shock waves in a liquid if we're moving at a high enough velocity. Okay. Yes. Mm-hmm. It's making the density, well, we're going to deal with this in depth in chapter, I think it's 9, but it will make, at first, it's going to make the density of air quite a bit higher, right? So the air is going to be compressing, right? So imagine, so you have a plane moving at Mach 5. So the example of like an aircraft moving at Mach 5, the airplane's moving through the air faster than the air can get out of the way. That's basically what it means. So it's moving through the air, in this case, 5 times faster than the air can possibly move out of the way. And the response is that the air kind of builds up in front and you get an increase in pressure in front. Yeah. Okay, any other questions? I saw a question, Tata, you're good, okay. Okay, and we will talk quite a bit more about compressible fluids later in the text. But for now, we're going to be generally dealing with, we're often going to be dealing with incompressible fluids. And for most of the first part of the class, we're going to be dealing with incompressible fluids, and that can include gases. Okay, so that's the important concept here. It's that gases can be treated as incompressible. So if we have a, sort of a conventional aircraft, like a small Cessna, like a single dual-seater airplane or something, they travel pretty slow. I mean, fast relative to cars, but still slow relative to speed of sound. And so we could model them as incompressible. Passenger jets kind of hover on that line of, they're not breaking the sound barrier, but they're getting to the point where we have to start considering compressibility effects. Okay, but there's a wide range of speeds over which we can consider gases incompressible. Yeah. The pressure from the air definitely affects the velocity of the aircraft. Yeah, so the pressure created by the aircraft traveling faster than the speed of sound definitely affects the velocity of the aircraft. That is an aerodynamic topic that's well beyond the subject of our fluid mechanics and chem E class, but definitely, yeah, that would definitely affect like the power you need to drive the airplane. Then, any other questions? Okay. Yeah, and in a pistol shrimp claw, we have compression of of water to such a high degree that the density would actually change. But this is a pretty extreme environment. So the idea is like, has anyone seen these like a pistol shrimp or a mantis shrimp? Have people heard of these? Yeah, crazy animals. So the basic idea is they have this claw that has a little plunger that goes into right in one section of their claw that meets with the bottom piece, and they snap it. Right, they snap this top piece into that bottom piece. Well, the snapping is actually the ejected fluid. So as they do this, fluid comes out, and the fluid moves so fast it creates a cavitation bubble. And then as that cavitation bubble collapses, it creates a popping sound. And they use it to stun prey. But if you look at the amount of pressure that's being generated as they're squeezing this claw shape together, it can get very extreme to the point where compressibility of water would become important. But we're not generally dealing with such extreme cases in this class. Okay. I think in an engineering situation, if this is happening, you might have a problem. Yeah. Okay. So for an incompressible fluid, right? So we're going to start off with our statement of mass balance from Reynolds transport theorem. ddt is 0, right? Rho is constant. But if we look, right, so that's just like our steady state assumption. But if we look at this term, that means we can pull density out of the integral, right? So we pull density out of the integral, and density is a constant, so it actually drops it out, right? And now this integral of v dot n over our control surfaces has to be equal to 0. So if we have uniform or 1D inlets and outlets in an incompressible fluid, it tells us that the sum of the flow rates, the volumetric flow rates in, has to equal the sum of the volumetric flow rates out. So Q here being volumetric flow rates, found as velocity times area. Right, so sum of the volumetric flow rates in has to be equal to the sum of volumetric flow rates out for an incompressible fluid. So one thing I just want to draw your attention to here is something that's a little bit strange, right? So we started with mass conservation, and then the mass piece, the density, drops out. And what we're left with is a statement solely about velocity and area. A little bit weird, but very nice for solving problems, right? This is going to make our lives a lot easier when we're solving problems, or a little bit easier, right? We don't have to deal with density and its units and so on. We're going to see a similar thing when we derive differential equations of fluid motion, the Navier-Stokes equations. We're going to see a similar kind of thing happen, where for an incompressible fluid, density is going to drop out, and we're going to get something solely in terms of velocities, which is initially kind of strange, but if you consider that if the density is not changing, then something like this must be true, right? Inflows equal outflows. So again, if the inlet is not uniform, meaning not 1D, then we have an integral. But again, this integral does not involve, we have an integral to find the volumetric flow rate. This integral does not involve the density, because we're talking about volumetric flow rate. From this expression, we can actually get something or figure out what the average velocity of a fluid is if it's non-uniform. So say the average velocity is just the flow rate divided by the area. And so it would look like this: 1 over a integral of v dot n dA. Right. So if I give you the velocity profile, you can use this to find the average velocity. Okay. This will come up. Yep. CS is control surface. Yes, CS is control surface, as it was previously. Okay. And if we define our average velocity in this way, then we can re-express our mass balance. Even for a non-uniform flow, we can now write our mass balance as the sum of the average velocities times areas out is the sum of average velocities times areas in, right? So for our mass balance, what this is saying is that for non-uniform flow, we can take this very simple form of mass balance and just use average velocities here. Okay. This is not going to always be the case for momentum and energy. That's why I'm drawing your attention to this. But for momentum and energy, we're going to have, for non-uniform flow, we're going to have some extra terms in here. Foreshadowing, I guess. Okay. So to look at an example, let's say we have this situation. We have two inlets, 1, 2, one outlet, 3. And the question for you is mass balance satisfied in this flow? And we're going to assume it's steady state, fixed control volume, 1D or uniform inlet and exit flows. We're going to ignore the energy right now. We'll deal with that. We'll come back to that in a second, or actually not in a second, potentially on Friday. And you're given these densities, velocities, and areas. So how would we get started here? If I ask you whether or not mass balance is satisfied within this flow, what would you do to get started? Start with what? Multiply velocity times the area, right? So velocity times area out is equal to the sum of velocity times areas on the inlet. Okay, so you're right, because density is constant, we're assuming this fluid is incompressible. It's all about the velocity in the areas. So I'm going to have V3A3 is equal to V1A1 plus V2A2. Then if I plug this in, I'll see that in this example, in fact, mass is conserved. Okay, the two sides are equal to each other. Okay. All right, any questions on mass balances? Okay, so now we're going to move on to momentum. And we're going to let our B, our quantity B, is going to be equal to the momentum of the fluid, which is a vector. It's going to complicate things a little bit in our momentum balance. So our quantity B is now a vector. Our quantity beta is now just the velocity field. Okay, remember beta is dB dm. So the amount of momentum per unit mass is just the velocity. Momentum is the mass times the velocity. Amount of momentum per unit mass is velocity. Now, if we take this, and one other thing that we have to note here is that momentum is not strictly conserved, but it will change according to Newton's second law. So some of the forces is mass times acceleration. This holds for a fluid as well as it does for a billiard ball. Okay, so some of the forces is ma. So we can change momentum of a fluid by applying a force. And if, for example, mass is something that can vary, then we could actually rewrite this for a fluid as some of the forces is dmv dt, where this mv is momentum. Anyway, momentum can change because of the application of forces, right? So forces applied to a control volume will act as a source or a sink of momentum. Okay, that's the key concept, really. I want you to get away from this slide. Forces applied to a control volume act as a source or a sink of momentum. So in our balanced equation for momentum, we're going to have to keep track of not only how momentum flows through the fluid, but also what forces are being applied to potentially change the momentum of the fluid. Okay. So for a stationary control volume, we can plug this, beta is equal to V into our expression of the Reynolds transport theorem. and develop this. Incidentally, this is why I was using this weird V for volume. Just basically getting ready for this piece here. And if I use standard V here, I think this gets a little bit confusing. So if you're writing this out by hand, I see many of you taking notes, which is good. It's hard to make a bold, like use bold notation. So just another reminder on vector notation. We can use an over arrow is a standard way of denoting a vector quantity. So on my slides, I'm often following the convention of your book. I'm using bolded quantities to indicate a vector field. But we can use over arrows as well. So for example, on an exam or a homework, if I'm asking you to find the vector velocity, I expect you to be writing it out as a vector. So that notation, this kind of notation is fine. Another note about the unit normal. So unit normal is the vector, right? Indicating, remember, the direction of a surface, right? So we define the direction of the surface based on the unit normal. So my water bottle is pointing in the direction normal to the surface of this table. If my water bottle had a length of 1, just non-dimensional length of 1, then it would be a unit normal vector for this surface of this table. Sometimes you will see this written as n in vector notation or n hat, that little hat indicating that it is a unit vector that has a magnitude of 1, a unit vector. Yes?
Here, the kind of squiggly V is velocity, and the bird light V is volume, right?
Yeah, so this is velocity, a vector quantity. This thing is volume. That's correct. Yep. Yeah, I did curly V in LaTeX, and this is what I came up with. Your textbook has a better font set or something installed as a better curly V. Should probably fix that. Any other questions? Okay. So if we allow the control volume to move at a constant velocity, then actually I'm just going to replace these. I can replace all of these with the velocity relative to that moving control volume. Okay. So as long as I'm moving, as my control volume is moving at a constant velocity, then I can use VRs in all these different places. Okay. So where VR is velocity relative to the control surface or control volume. If we're in a non-inertial, meaning an accelerating coordinate system, this would change. We have to deal with the acceleration as it's experienced by the fluid. We're not going to discuss this in this class. Your book has more details on how we deal with this, but we will not be discussing this in this class. I should note that we are all in an accelerating coordinate system right now because the Earth is rotating, right? So we're all experiencing a Coriolis force. The magnitude of that, of the effective force that we're all feeling because of the rotation of the Earth, or the magnitude that would be felt by the air in this room, for example, because of the rotation of the Earth, is something like 10 to the minus 5 G, right? So much, much smaller than acceleration due to gravity. And so over the length scales of the kinds of flows that we're going to consider in this class, it's not really going to be important. But if you're doing like atmospheric physics, definitely important. It's definitely important in that case. Yes.
So we dealing with accelerating, is that more like a ground level course, or do we get to that later on?
That would be a ground level course. That's not going to be covered in this course. Yeah, yeah. Good question. Or if you're going to go work on a rocket ship, then right, which I mean, some of you may, especially given local industry. But in this course, we won't be covering them. Okay, so some other notes about the momentum balance. When we say some of the forces, we mean all the forces acting on the material. We're going to account for all of these. But this could be body forces. So for example, gravity, where by body forces, I mean something that acts on the volume of material of the fluid. So if I have a small fluid element and it's in a gravitational field, right? It's on Earth, for example. It is experiencing a gravitational force that's proportional to its volume. That's a body force, like gravity. And these forces also include surface forces, like pressure and shear stress. So forces that are felt at the surface of a fluid element, compressing it or resistance to shear. So viscosity, for example, is going to enter into the equation for momentum. Another note, just as a reminder, this is a vector equation, right? So this means that this one equation is kind of sneakily hiding three, one for each component. So, one for X, one for Y, one for Z. So when we've written this out, we've actually written out kind of three things, but compressed it all using vector notation. I mean, generally, when we're solving problems, we're going to split it back out into those three components, X, Y, and Z. And sometimes I might ask you just something about X, or you might only be interested in something about X, but sometimes you're going to have to use two or even three components of this set of equations. Okay, so it's kind of a set of equations, not really just one. Yes. So the question is about resources for example problems. I mean, the homework, I'm trying to give you example problems that are similar to the types of things that I want you to know. I'll also give you problems from past exams to show you the types of things that I want you to know. Prior to exams, I will give a list of the extra example problems from your text. In general, the problems in your text are pretty good. And it's the even numbered or the odd numbered. Half the problems in your text have answers, like numeric answers in the back, which you can use. Is that what you mean, or what other examples do you mean? Yeah. So question for the recording is, are there videos where you can see someone working through it? I have some videos where I've worked through a few problems. As I said, I'm kind of building my catalog of those, so I'll add more as we're getting towards the exam. If you go to the pages section on Canvas, that's where I put up the video. I put up pages with embedded links to all the videos we talk about every week. But I also put in a page with like general course videos that you might be interested in. And there's some lectures from Brian Story, who I think does a pretty good job of explaining problems, and he goes through some momentum examples, actually. I think in one of the videos that I've linked to on that page. If you're having trouble, just email me and I can send it to you. Okay. Does that answer your question? Okay. Take a look and let me know if it doesn't. Any other questions? Okay. And we will go through, some of this in class, and you'll have practice on your homework as well. And you can come to office hours. Okay, so let's look at X direction, right? Let's look at just the X direction. Right, so this is one of the three equations buried within that vector expression. Basically what we're saying is that some of the forces in X is going to be balanced out by the change of momentum within the control, X momentum within the control volume, where I'm denoting the X component of velocity as U, plus the amount of X momentum, U times rho, that leaves the control volume through my control surfaces. So forces in the X direction are balanced out by any change in momentum within the control volume, plus momentum that advects or is carried by the flow into or out of the control volume. One strange thing here, which is often a point of confusion, I want to draw your attention to it. This is still vector velocity v dot n. Right? So what I'm saying, what this expression is saying is that X momentum can be carried into or out of the control volume by the full vector velocity v, not u dot n, but full vector velocity v. Meaning that what this implies is that x momentum can be vectored by velocities in the y or the z direction. So if I have, so imagine if I like throw my water bottle across the room, right? Throw it to Michael over on the other side of the room. It has a certain amount of x momentum, right, in it, because I'm throwing it across the room. And if I draw a control surface that's sitting right here, I'm going to be carrying that x momentum across that control surface, right? And that x momentum is carried across a control surface by the velocity in the x direction, right, of this water bottle. But now let's say instead I'm going to draw my control volume to be something like here, and I'm going to toss it up a little bit as well. Right, so now I have a control surface which is no longer perpendicular to my x direction. Now the x momentum, the component of the velocity times the mass, in this case of the water bottle, in this direction, is going to be carried across this control surface by the component of its velocity that is traveling vertically. So the momentum of water bottles within my control volume, right, in the x direction, will be decreasing, right, within my box, right, within my control volume, because it's being carried across the control surface by its velocity in y. That makes some sense? Yeah, sure. Yeah, no, this is always a point of confusion. I'm always looking for a better explanation of this. So we're trying out a new one this year. So, okay, let's say I have this water bottle and I'm throwing it across the room at some fixed velocity, right? I throw it across at 2 meters per second or something. It has a certain mass, it has a certain velocity, it has a certain x momentum, right, as it's traveling across the room. It makes kind of intuitive sense that that x momentum, if I draw a box here, right, say this is my box, and if I throw it just horizontally, then that x momentum will be leaving this control volume because of the x velocity of the water bottle, right? But if I also give it some y velocity, let's say I give it the same 2 meters per second, so it has the same momentum in x, okay? But now I also give it a y velocity of 2 meters per second, okay? Now it's going to leave my control volume through this upper surface. But as it leaves, it is still carrying the same amount of x momentum, right? That same 2 meters per second times the mass. It's just being carried across this control surface by the it's being carried out of the control volume by the y velocity, not the x velocity. That makes sense? I heard some good noises, I think. Yeah.
Are we saying like we have an imaginary square that will lead through, but it like dodges it when it was open, so like it doesn't have any excellent when it leaves, like left at the top of the side.
It still has the same, this thing is still traveling at the same, it has the same same x component of velocity, 2 meters per second, right? No matter whether I've added y velocity or not. And so as it leaves, it's carrying the same amount of x momentum with it. It's just that that x momentum is either carried out by the x velocity or by the y velocity. So we can return to this, and we'll return to this in examples as well. Yeah. Yeah, I think they often don't work. Natalie, yeah. Yeah, that's exactly it, right? So if let's simplify to a ball instead of the water bottle. So if this is moving at 2 meters per second, right? In this case, it has some mass m. If it travels at 2 meters per second out of this control volume right here, then the momentum of this ball leaves the control volume because of the x velocity, right? It's advected in fluid terms, it's advected out of control volume by the x velocity. But if I now also give it a 2 meters per second velocity in y, such that it now travels up out of this control surface, then I'm losing the same amount of x momentum as it crosses this surface. But that x momentum is lost from this control volume because of the effect of the y velocity. I mean, let's consider that this is my control surface, my control volume, right? So there's no way for the x velocity to carry it across that control surface. The only way for this x momentum to leave the control volume is because of this y velocity. That makes some more sense.
So essentially, we're losing mass in the control volume, and because that mass is not accounted for in the control volume, we don't have that momentum in the control.
In this example, where it's not a fluid, it's a solid, we are losing mass as well, right? In a fluid, we can maintain mass, but lose momentum. So I want you to think of this in terms of momentum, right? So this object has momentum, and it has, in this case, an x momentum, and we're losing that x momentum because of the influence of this y velocity, okay? Yeah, so the integral, yes, the control surface is wherever the momentum is lost, okay? And we note that we have, for this x component of our momentum balance, it's u times rho, right? X component of velocity times rho times the full vector v dot n. Okay, it tells us the rate at which we're losing momentum through those control surfaces. Okay. So if we have something moving across a control surface at an angle, like the ball or the water bottle or something, then we will we can lose x momentum because of velocity in y or z. And there was an example that I linked to last time, which I'll link to again, where I worked through a problem with where we're losing x momentum because of velocity at an angle. So because of a y component of velocity. So in many cases, we're going to simplify momentum equation to uniform flow, just like we did for our mass balance. The expression then becomes sum of the forces is rate of change of momentum within the control volume, plus the sum of the momentum that's leaving minus the sum of momentum that's entering. Again, outflows add, inflows subtract, because this is a balance equation. So if we apply more force, if we're applying a force, it means it has to balance out somewhere. So momentum is lost via outflows that are balanced by applied forces. And so any momentum we lose from outflows has to be balanced by application of force within the control volume. One note is that we do have to be careful with this 1D or uniform flow simplification. Because in many cases, if we look at this quantity here, for example, this is the x component of momentum being advected by the flow across a control surface, u rho v dot n dA. In many cases, this is not simply equal to m dot times the average velocity, which is what you would assume in the uniform velocity case. Or this is what you would assume by analogy to the, the mass flow case. And one way to handle this is to apply what your textbook calls momentum correction factor, using this Greek letter zeta. In this case, we would rewrite this expression and say that this is equal to some geometric correction factor zeta times m dot the average. And notice that for parabolic flow, which we're going to consider within pipes when we deal with pipes, this factor is about 4/3. So you're off by about 33% if you don't use this correction factor. When we get to turbulent flow, it's going to be slightly faster flow within pipes, that correction factor gets smaller. And for uniform flow, that correction factor is just 1. So this means for non-uniform flow, we can simplify this expression. Sum of the forces is the rate of change within the control volume plus the sum of our momentum correction factors times m dot times v average on the outlets minus the same quantity on the inlets. So we're going to pick up from here on Friday after a brief discussion of a few videos. We'll look at, for example, the assumption of steady state, and we'll see what simplifications that gets us. All right, thank you all.